So just maybe a few things before we start with the webinar. So this meeting is being recorded. So yeah, we will also receive the recording after the webinar so that you can yeah, have a look at it again. Also, I want to ask to post your questions or ask your questions at the end of the webinar. So that's why you also are muted. And you can raise your hand or you can post them in the chat, and then we'll try to answer them at the end of the webinar. And then we can also unmute you so that we can discuss. So I'm Jeroen Jordens. I'm a senior research engineer at Flanders Make, and I'm working in the circular joining technology domain. And we're doing mainly research about adhesives, adhesive bonding processes. And today I will present a webinar about design for circular adhesive joints. Now, if you're talking about design and circular, often eco-design is another term or terminology that is often being used. And adhesives and eco-design, is that not a contradiction? You can ask, because if you look at the eco-design directives, somewhere, or it's often stated like products should be designed to be easily repairable and upgradable. And if you look at adhesives, yeah, is this not in conflict? Because adhesives typically, once they're cured, it's very difficult to debond them, to separate the materials that are bonded. And should we not use detachable joints such as bolts, for example, in this case? Well, in this webinar, we'll show you that this should not necessarily be the case. In some situations, it might be better to use bolts, for example, or other joining technologies, but there exist also solutions to make adhesives more circular and to make them fit into a kind of an eco-design or a circular economy, and to allow for easy repair and upgradability. So how do we think that adhesives would fit in a circular economy? Often, if you think about circular economy, they refer to the 9R principles, which are also shown in this figure. And we think that adhesives or circular adhesives could fit into sections. One is the reduced section. So you could select a more sustainable adhesive. One, if you're using already an adhesive, you could go for example, a bio-based adhesive or an adhesive with a lower carbon footprint, and hence reducing your environmental impact. Or you could also select an adhesive and design your adhesive joint in such a way that it allows on-demand debonding and rebonding. And this will facilitate the separation or detachment of the materials that are bonded, and hence you will also facilitate or have easier repair, refurbishment, and remanufacturing. Now, during this presentation, I will focus on these two parts, but I will start first with giving a few advantages and disadvantages of adhesives, so you have an idea, okay, in which situations can I use adhesives, or are they beneficial, and in which situations they are not. Then I will talk about sustainable adhesives and how we can make them more sustainable, or can select more sustainable adhesives. Next section will be about the debondability. So how can we debond adhesives on command? And then finally, we'll end with the expertise that we have at Flanders Make. So how can we support you in this process? Now, if you think about advantages of adhesives, one of the biggest advantage is that they allow for a uniform stress distribution. So you don't have to drill a hole in a material or in a panel to insert a bolt, for example. You can have a very uniform stress distribution, and because of that, it's often possible to go for thinner materials and lighter materials. So, for example, composite materials, which are much lighter typically than metal materials, which they replace. They allow for good weight savings, and they're also a perfect match with adhesives, and it's much more difficult to join them with other joining technologies. It's also possible to join the similar materials with adhesives, like, for example, in the picture, you have glass and you have steel or aluminium. They might have different thermal expansion coefficients, and adhesives are able to deal with this. So that's not per se a problem. They can also seal joints, so not only join them, but also seal, so close a gap from air or water or chemicals. They can dampen vibration to a certain extent. And you can also play with the properties of the adhesive to make them electrically or thermally insulating or conducting. So by adding different fillers, you can play with it. And for example, if you think about the batteries of electrical vehicles, and you want to have fast charging batteries, you can adhesives which are thermally conducting are often used to facilitate this. So because they can really transfer the heat very efficiently and very fast. And then also corrosion prevention is an advantage. So you can avoid that two metals, for example, come into contact with each other and start corroding. It's also possible to create an aesthetic invisible joint. So because you don't have to drill holes, but you also don't need access to the joint. So that's also an advantage. And it also allows for higher design freedom because of the above mentioned advantages. Of course, there are also disadvantages or challenges related to adhesives. One is that they're sensitive to aging and degradation. So they're sensitive to weathering conditions like moisture, UV radiation, temperature fluctuations. They're also sensitive to heat. So for example, if you have an application where you need 1000 or 2000 degrees Celsius, maybe adhesives are not the best solution. It's also difficult to test the strength of the bond non-destructively. So it is possible to test the strength, but then you break the samples typically, or you break the material. Non-destructive tests, they cannot tell you a lot about the real strength of the bond. So that's a challenge. And you need a kind of a drying or curing time. So for example, once you join the materials, you need to fixate them for a certain time before they're fully cured or they reach a certain strength, and before you can move the joint parts. And then you also, adhesives come with an environmental impact. So they're made of chemicals, and these chemicals can contain hazardous substances, for example, isocyanate, or they also often made or produced from fossil fuel-based chemicals, so they have a carbon footprint. And lastly, the challenging separation. So once they're bonded, it's for typical adhesives, it's more difficult to dismantle them, to repair and recycle them. During the remainder of the webinar, I will focus on the last two challenges, and I will show you how we can remediate them, or how we can improve them. If you look at sustainable adhesives, so improving the sustainability, then one solution could be that you select adhesives which contain less hazardous substances. So, for example, if you're working with a polyurethane, you could, one component polyurethane, typically you could select also an MS polymer which has similar properties. And the advantage is that you don't have isocyanate in it, so you don't need, for example, your workers to be trained for working with isocyanate. It's less hazardous. But of course, it comes with a cost drawback, so a higher cost. But that's an option. So just conventional adhesives, you could replace them by less hazardous other adhesives. You could also use bio-based adhesives. So for example, there exist bio-based or adhesives with a bio-based content up to 100%. And these are adhesives where the chemicals that are used to formulate them are coming from bio-based raw materials, so like lignin or like lactic acid. You also have adhesives with recycled carbon content, for example, Sudal, but also other suppliers have adhesives on the market with up to, for example, 80% recycled content. And here the chemicals that are needed to formulate adhesives are made from a waste stream of carbon. So they are recycled, and that can be, for example, recycled plastics or other carbon sources can be used, waste streams, to create these chemicals. Also, biodegradable adhesives exist, for example, in packaging. This is an example of a biodegradable hot melt. And that's one, once exposed to the environment, it will biodegrade, it will degrade over time. Now, if you look at all these solutions, typically there exist solutions for low performance applications. And what I mean with this is that the strength, for example, is typically at the lower end. It's low strength applications, or they're not exposed to very high temperatures or to chemicals or to weathering conditions, for example. So for these applications like packaging, there exist solutions. But if you look at the higher end applications, so the higher strength, the epoxy adhesives, for example, it's much more difficult. Maybe there exist a few examples, but it's much more rare that you find suitable adhesives there. And another thing that's important to mention, so we can focus on the sustainability of the adhesive itself, but often if you look at the full life cycle analysis of a product, the biggest environmental impact comes from the materials which are joined and not from the adhesive itself, because the volume of an adhesive is typically very low. So if you could achieve an easy debondability, then this will have a much higher impact than changing to, for example, a bio-based adhesive, which is not debondable maybe. So that's also important. And that's why, so the next topic will be the challenging separation. If we can solve this, this could really provide a benefit. And we could achieve this by creating a kind of a debondable adhesive joint. Now, what do I mean with debondable? Typically, you have an external trigger or an activating trigger, which can be heat, it can be radiation like UV light, it can be electricity or another source or a combination. And if this trigger is not applied, then your adhesive joint is intact and it has the same strength and the same performance as a normal joint. Once you activate the trigger, then it's easier to separate the both materials and the bond will debond. So, and in the ideal scenario where you have a circular joint, you could also apply a trigger for rebonding, and then you could rebond again. But that's only for a few adhesives possible. Now, what are the possible triggers? We divided them in three different categories or three different technologies. One is mechanical, so you could apply a mechanical force to debond. It can be pulling, shearing, or whatever. You could have a thermal trigger, so you could play with the temperature, like heating the adhesives up or cooling them down. And because the temperature changes, also the properties of the adhesive will change. There are different ways in which you can heat or you can play with the temperature. It can be convection, induction, microwave, laser, or infrared heating. Or you could play with electrochemical triggers, and that can be electricity, UV light, or chemicals. And then you have also some technologies which are a combination. For example, expandable particles. These are triggered by heat, by thermal energy, but they will expand and will create mechanical forces inside the adhesive. And now I will show some example, very high level, to give you an idea in which applications these adhesives are used and to show you what's available on the market. So mechanical debonding, the best known example, I think, is one of the windshield of a car. So if you go to a repair shop, for example, what they can perfectly debond the windshield, which is typically bonded with a polyurethane adhesive, and replace it. So what they do is they insert a kind of a separation wire. So that's the orange wire that you see here, and then they cut out the polyurethane adhesive, and they can debond your windshield, take it off, remove the adhesive, and rebond again. So that's not a problem. It's used on an industrial scale already. But this technology is, of course, not possible for all types of adhesives. So you can apply them in the case of a windshield of a car, but it's not that it's suitable for all applications, of course. Another example of thermal debonding is one where, if you look at the movie on the right, so you have a high strength under normal room temperature conditions. If you heat them, then they will lose a strength, and then just by hand, for example, you get debond. So this is an example of a hot melt adhesive. It's a bio-based reversible hot melt. And what's special about this hot melt adhesive is that it's actually a fully circular adhesive. So if you heat it, it becomes liquid and you can apply it. You can join both substrates or both materials together. And then when it cools down, it regains its strength. It solidifies. And then if you want to debond, you just heat up again and it will become liquid again. And that's something you can we do all the time. So in this case, Conagan used it for example, for textile adhesives, so for shoes. But yeah, there are also other applications like packaging that hot melts are used. Another principle of thermal debonding is a heat debondable primer or an adhesion promoter or an adhesive. And yeah, this is an example of TESA that you see in the movie. But so you can apply, in this case, an adhesion promoter on a substrate. You can see that under normal conditions it has a quite high bonding force. You cannot peel it off by hand. And then what I do is I heat it to 150 degrees, and then there are particles inside that are triggered. You see it becoming white. So that are the particles expanding, and then just by hand you can easily pull it off. So that's a kind of an adhesion promoter. And the nice thing is that now it's debonded at 150 degrees, but you can select the temperature at which it can debond. So but playing with the particles, you could select a range from 80 to 210 degrees Celsius on which it will debond. And also for some applications, we could use flame retardants, for example, so that also in case of a fire, it should not always be a problem. And that, it can resist flames, for example. We used this, just to give you a concrete example. So the leather was a kind of a tape that you see, an adhesion promoter. We use this principle for the projector lens, and that's typically a glass lens or a glass prism, which is bonded to an aluminum frame. And what happens at the end of the life, or they use adhesives here to bond it because the positioning of the lens is very important, so it should be very precise. And at the end of the life, the electronic components of the projector, they should be replaced, but typically the glass lens is still intact. It's still okay. There's nothing wrong with it, so you could reuse it. And actually, it's also quite expensive. So what we investigated here is, can we debond the glass lens from the aluminum holder and then reuse it in another projector, for example. So we did this by adding some of the thermally expandable particles. So we mixed some particles with the adhesive, and we bonded the glass lens on an aluminum frame. And just by heating it in an oven at 120 degrees Celsius for 10 minutes, you can see on the right side, it's accelerated, but you see that the adhesive starts foaming. It's the particles that are triggered, it's really expanding, and it starts foaming. And just with no mechanical force, both parts separate. And the nice thing is also that you can easily clean the lens. So it becomes really brittle. You can really scrape off the adhesive without any problem. While if you would mechanically debond, for example, you still would have problems with removing the adhesive. So that's an option, debonding with a thermal. I showed now some examples where you heat in an oven, but you could also use other technologies for heating, for example, induction heating or heat blankets, which are maybe more mobile. For example, Indar used this principle on a car. So they developed a kind of an adhesive which would debond with an induction heating device like you see on the left. And what they can do is then, so once you're at end of life, you trigger the adhesive, you heat up the adhesive with induction, and then you can separate the frame, for example, and the backlight of the car. Another example is of electrical debonding. So it's used in an iPhone 16 for the battery bonding. So they made a kind of a dummy battery, and you see it's a tape that they first apply on the dummy battery, I would say. Yeah. So they roll it so that you have a good adhesion to it, and then they remove the second layer and they place it inside the iPhone. So it's also a dummy, but just to show the principle. Then I will press it together just to make firm contact, so that you have a good connection and you have a good bond, I would say. And then I will show you that under normal conditions, you have a quite strong bond, so you have a good connection. You cannot peel it apart manually. So here I will show that I can go up to, I think, 80 Newton by hand, and it does not debond. And then I will debond it by electricity. So they will put electric voltage over the adhesive, 12 volt for 60 seconds. So it's quite fast. And then the adhesive is triggered. it will debond, and then you will see in the next phase that you can easily debond, so by hand without any force. So this is an example of electrically debonding adhesives. So there are special adhesives designed for debonding, and yeah, they claim you can use it in cell phones, car displays, battery LEDs, etc. So this is one of data, but there are also other suppliers using it. Another example is chemical debonding. So here, this is an example of Centrexa, where they used a kind of adhesive to bond and debond on a military vehicle. So they have a LiDAR array there, and they want to add and remove filters on this LiDAR array. And they created a kind of adhesive which could be debonded by an aqueous debonding agent. So a special chemical agent, if the adhesive comes into contact with this chemical, it will debond. If it's in contact with other chemicals or normal water, it will not debond. So this is just an example of an application there. Now, during this presentation, I showed you a lot of different possibilities, different debondable adhesives. It can be that you're a little bit overwhelmed. So, okay, which adhesive do I now select for which application? And that's something where we can support you in Flanders Make. So we look at the bonded product life cycle, and we can support you in the different phases. So for example, in the design phase, which we can support in selecting or answering the question, which circular joining technology should I now select? Which adhesive should I select? How should the bond look like? We can also test it, so we can validate or make a prototype, and we test it in our climate rooms. And we can also support in the production and the end of life phase with how do I apply now this solution, this adhesive, and how do I dismantle it. So to make it a little bit more concrete, so first phase, selection of circular joining technology. So we have a team of European adhesive experts, and we can support you with a supplier independent selection of an adhesive there. So we have their expertise. We can also support you with the design of the joint. We can support you with some finite element modeling or simulations if you want. But also experimental validation. So we can also test this adhesive on your materials, for example, in our climatized test bench in our climate room, where we can expose it to UV light, to temperature, to moisture, so different weathering conditions. And we can do also accelerated aging tests to really prove that or to test if the adhesive can resist these conditions. And also microscopy or fader analysis is possible on the final product. And finally, bonding and debonding, process optimization. So we can support you with selecting which are now the process steps. How should I bond it? What are the optimal process parameters that I should use? And we can also make a kind of a demonstrator to really prove on your product, for example, smaller full scale, that you can debond, for example. And it can go to full scale. We've, for example, a windshield of the car, we have also made a demonstrator for this in the past. So it can go to a larger scale as well. Now, the last slide, I want to present two projects which we're working on. The first one is one about together with Vito, and it's about the development of a low carbon footprint debondable structural adhesive. It's an ICON project. And if you remember in the beginning of the presentation, I presented that, or I told you that for the low-end applications, so with the low strength adhesives, there exist already solutions, and there are solutions on the market. But for the high strength applications, or the applications where it should be resistant to chemicals or high temperatures, etc., there are not so much commercially available adhesives, and that's what we want to investigate here. So together with Vito, look at or to develop these low carbon footprint adhesives. So we'll start from a low carbon footprint raw materials like lignin or recycled carbon. We'll develop adhesives, and then we will test them in industrial applications. We're thinking about construction or automotive or industrial applications. And yeah, then we also want to test the debonding of the adhesive at the end of the life. And we want to see if it's technically feasible, environmentally and economically feasible during this project. A second project is one together with University of Ghent and Hasselt. So there we want to see if we can use AI for product design and process design optimization. So typically AI relies on big data. So that's data with large volumes of data, which is very cheap to achieve. And typically that's not what you have available in industrial climate. So typically you don't have a lot of data. It's rather small in quantity, but the quality is often higher. And that's what we want to investigate here. So how can we use the data efficient machine learning or data efficient AI technologies for the product design? For both projects, we're still looking for companies to join a consortium. So if you're interested, just let me know. You can find my contact details here, and then we can have a discussion or meeting to discuss about the project. Also, if you have other questions about the circular adhesive joints that I presented today, or you have a particular case that you want to discuss with us, don't hesitate to contact me, and then we can schedule a meeting or we can arrange a visit to our labs here in Lommel. That's not a problem at all. And I think that we then, that's a presentation, the webinar. So then we can move to the questions if there are any. So are there any questions from the audience? I didn't have a look at the chat or the.
Hello, Jeroen.
Hello.
I may have a question for some. It's a very simple product. It's made out of polyprop sheets, very well, easy to recycle. But as you know, adhesives can, yeah, it's only a small margin of putting extra material to it. But is there adhesive that has been made out of polyprop-ish materials, so everything stays kind of virgin, or is that yeah, an utopia? I don't know.
So you mean an adhesive which would not hinder the recycling of polypropylene in the end, so that you don't need to separate, or?
Yeah, so the virgin material stays, yeah, let's say 100% virgin.
Yeah. Yeah, as far as I know, I'm not an expert in polypropylene adhesives or recycling of polypropylene, so I don't know exactly, for example, how the recycling process of polypropylene works. So at this moment, I cannot really answer the question. So it depends a bit on what chemicals, for example. If it should be fully polypropylene, I would think then, yeah, maybe you can do a kind of a plastic welding instead of using an adhesive, because then you're only using polypropylene. If there can be chemicals mixed with the polypropylene and they will not hinder the recycling process, or they can be taken out in the recycling process, that's something I don't know yet, because we're not really working on the recycling of on adhesives. We're mainly working on the bonding itself. So yeah, that's something I cannot answer at the moment.
Okay, no problem.
Other questions? I see one in the chat. So hello, thank you for the presentation. Can you propose examples of sustainable adhesives that can withstand high temperatures, so 250, 350 degrees, for glass metal bonding? Yeah, I think it's always dependent on application. So now you're just stating the temperature. I know that some epoxy adhesives, for example, they can withstand high temperatures, but I will not say that these are suitable, because it really depends on also the other boundary conditions. So if you have something in mind, I propose that you arrange a meeting, or that you post your contact details so that we can arrange a meeting. But typically 250 to 350 degrees for some applications, for example, in aerospace, there exists solutions which can resist high temperatures, or adhesives which can resist higher temperatures. But it depends, of course, what the real conditions are. So what strength, what other boundary conditions it should be able to withstand. What's the so that's something we should then, I think, discuss. And it's not something I can give an answer to right now on the spot. Okay. I see Mohammed is still typing. Anybody else who has a question in the meantime? Yeah, so Mohammed, you can definitely contact me. So my contact details are were in the presentation. So we will also send the presentation or the recording around, so you can still find my contact details there. There's also kind of a link to a feedback form. So if you want to answer or to give some feedback about the webinar, that would also be very helpful for us to see what we can improve in the future. So we'll also send that around together with the recording of the webinar. If there are other questions, I propose, you just send me a mail and then we can discuss afterwards, if that's okay. Good. Then I think we can close the webinar here. Thanks a lot for listening, and see you.